A 15,000-ton coal train on a 3% mountain grade is a physics problem, and the answer cannot be air brakes alone. If it were, the brake shoes would be glowing orange within a few miles, the iron literally melting from friction. Working brakes, doing exactly what they are designed to do, destroying themselves before the bottom of the grade. This is the story of what actually stops a heavy freight train on a mountain descent, and why the answer is not what most people expect. Before anything else, you need to feel what 15,000 tons actually means. A loaded coal hopper wagon weighs around 130 tons. A typical heavy coal train on a mountain route might run to 120 of them. Add the locomotives at the front, typically 3 or 4 units each weighing around 200 tons, and you are somewhere around 15,000 to 16,000 tons of moving mass. Now consider what it takes to stop that mass. The kinetic energy of a moving object increases with the square of its velocity, which is the physics way of saying that doubling the speed does not double the energy you need to absorb to stop it. It quadruples it. A train moving at 40 miles per hour does not need twice the braking force of one moving at 20 miles per hour. It needs 4 times as much. On a flat surface, this is challenging but manageable. A well-maintained air brake system on a modern heavy freight train, applied correctly and in good time, can bring the consist to a controlled stop within reasonable distances. On a 3% grade descending a mountain, the physics change completely. A 3% grade sounds gentle. It means the track drops 3 feet for every 100 feet of horizontal distance. Over 10 miles of descent, the track falls 1,584 feet. The potential energy that a 15,000-ton train loses as it descends that grade has to go somewhere. The place it is supposed to go is the braking system, and the braking system has limits. The air brake system on a freight train is one of the more elegant pieces of engineering in transportation history, and understanding its elegance helps explain why it is not enough on its own for heavy mountain descents. The system was invented by George Westinghouse in 1869, and the core principle has not changed since. A continuous train pipe runs the full length of the train, connecting every vehicle. The pipe is kept pressurized to around 90 pounds per square inch by compressors on the locomotives. At each wagon, a triple valve monitors the pipe pressure. When the engineer reduces pressure in the pipe by opening a valve in the cab, every triple valve on every wagon detects the pressure drop simultaneously and applies the brakes. Release the pipe pressure and every wagon brakes. Restore it and they release. The genius of the system, which Westinghouse recognized immediately, is that it is fail-safe. If the train pipe loses pressure for any reason, whether through brake application, a burst pipe, or a broken coupling separating the train, every wagon applies its brakes automatically. A loss of pressure means brakes on. You cannot accidentally leave the brakes off. But the system has a thermal limit that no amount of clever engineering has ever fully removed. Friction produces heat. The brake shoes press against the wheel treads and slow the rotation, converting kinetic energy into heat. That heat has to go somewhere, and it goes into the brake shoe and the wheel. Both have thermal limits. Cast iron brake shoes begin to lose effectiveness above a certain temperature. At high enough temperatures, they begin to break down physically, the material softening and ablating in a way that reduces braking force precisely when braking force is most needed. Wheels can develop thermal cracks from repeated heating and cooling cycles. In extreme cases, wheels can fail catastrophically from heat stress. A heavy train descending a long mountain grade and relying solely on air brakes is feeding energy into this system continuously. If the rate of energy input exceeds the rate at which the heat can dissipate into the surrounding air, the system heats up. And as it heats up, it becomes less effective, which means the engineer has to apply more braking force, which produces more heat. The feedback loop is not difficult to see. If you are finding this useful, subscribe now. Every week we cover the engineering that keeps these machines running and the moments when it does not, which is why heavy freight trains on mountain grades use something else as the primary braking system and reserve the air brakes for supplemental and emergency use. Dynamic braking. And it works on a principle that is almost counterintuitive once you understand how diesel-electric locomotives operate. A diesel-electric locomotive drives its wheels through traction motors, electric motors mounted directly on each axle. The diesel engine drives a generator. The generator produces current. The current powers the traction motors. The traction motors turn the wheels. That is the normal operating mode. In dynamic braking, the engineer reverses the electrical relationship. The traction motors are reconfigured as generators. The wheels turn the motors generate current, and that current is fed into banks of resistors mounted on the roof or sides of the locomotive, where it is dissipated as heat into the airstream. The motor that was driving the wheels now resists the rotation of the wheels, slowing the train. The train is braking, but the brake shoes are not involved at all. The energy is being absorbed electrically, converted to heat, and shed into the air. The practical advantage of this is enormous on a long descent. The resistors can absorb enormous amounts of energy continuously without the kind of thermal degradation that friction brake shoes experience. The locomotive can sustain dynamic braking for as long as the descent lasts. The brake shoes stay cool, the wheels stay cool. And when the air brakes are needed for trim control or final stopping at the bottom of the grade, they are available and effective. On a modern heavy freight locomotive, dynamic braking can produce a braking force equivalent to several times the locomotive's maximum traction effort. The Canadian Pacific and the BNSF both operate mountain grades where dynamic braking accounts for the vast majority of energy absorption on downhill runs, with air brakes used only for fine control and emergency stops. So if dynamic braking solves the thermal problem, why do runaway trains still happen? Why are there still incidents of heavy freight trains losing control on mountain grades despite decades of engineering refinement? Because the system depends on the locomotives being at the front of the train and functioning correctly. And not all heavy freight train configurations guarantee either of those things. On a very long heavy train, the locomotives at the front are pulling or braking that consist through the couplings. The forces transmitted through a coupling chain on a 15,000-ton train under dynamic braking are enormous. On a steep descent, if the train is longer than a certain point relative to the grade, the rear of the train can push against the front faster than the locomotives can absorb the energy through dynamic braking alone. This is called a runaway or a train separation event, and it is one of the most dangerous situations in heavy freight railroading. The train does not lose its brakes. It loses the fight between the braking force at the front and the gravitational force pushing from the rear. The solution that the industry developed over decades is distributed power. Rather than placing all the locomotives at the front, some are positioned in the middle of the train or at the rear, connected to the lead locomotives by radio control systems. The rear and mid-train locomotives apply dynamic braking in coordination with the front units, absorbing energy along the full length of the train rather than fighting the entire gravitational load through couplings that were never designed for the forces that a 15,000-ton train on a 3% grade can generate. Union Pacific, BNSF, and CN all operate distributed power systems as standard on their heavy mountain runs. The radio links connecting the remote units to the lead locomotives are monitored continuously. Loss of the radio link triggers automatic brake application. The system is designed so that any failure moves the train toward a safer state rather than a more dangerous one. There is one more problem that the elegant simplicity of the Westinghouse air brake system creates, and it is one that engineers manage every day without passengers or observers ever being aware of it. When the engineer applies the brakes by reducing train pipe pressure, that pressure reduction does not reach every wagon simultaneously. It travels down the train pipe at around 900 feet per second, which sounds fast, but on a train that is 1.5 miles long means the brakes at the rear of the train apply around 8 seconds after the brakes at the front. 8 seconds does not sound like much. But in those 8 seconds, the rear of the train is still traveling at full speed, while the front is beginning to slow. The train is compressing. The couplings between wagons, which have a small amount of play in them, are being pushed tight as the rear catches up with the front. This is called buff force, and on a heavy train applying emergency brakes, the buff forces that develop can exceed the structural limits of the wagons and couplings. An emergency brake application on a heavy freight train at speed can, if handled incorrectly, derail the train it is trying to stop. Engineers on heavy mountain trains apply brakes in a specific sequence and at specific rates to manage this slack. A reduction of 6 to 8 pounds per square inch in the train pipe pressure applies the brakes throughout the train with enough force to control speed without creating dangerous buff conditions. Full emergency application, dropping the pipe to zero, is reserved for genuine emergencies because the consequences of mismanaging the resulting slack action can be severe. This is why train handling on a mountain grade is a skill that takes years to develop, and why automatic train protection systems that override the engineer in certain conditions are a significant safety investment across the major freight railroads. The physics is manageable, but it requires continuous attention and correct judgment from the moment the descent begins to the moment it ends. So here is the complete picture of what is actually happening when a heavy freight train descends a mountain grade. The air brakes are working. The system that George Westinghouse invented in 1869 is functioning exactly as designed, keeping pressure throughout the train pipe, responding to the engineer's inputs, holding the consist at a controlled speed. But the air brakes are the backup system on a mountain descent, not the primary one. The primary system is dynamic braking, absorbing the train's potential energy electrically and shedding it as heat from resistor banks on the locomotive roof. Distributed power units in the middle and at the rear of the train are applying dynamic braking in coordination with the lead locomotives, managed through radio links that the crews and dispatchers monitor continuously. The engineer is making brake pipe adjustments in increments of 6 to 8 pounds, managing the slack in the train's coupling so that the rear does not run into the front, so that the buff forces stay within the structural limits of the consist. None of this is visible from the outside. From a distance, a heavy freight train descending a mountain grade looks exactly like one going across flat ground. But inside that consist, the traction motors are generating current and feeding it into resistors that are getting hot enough to glow. The couplings are cycling through tension and compression as the slack breathes. The train pipe is holding at a precise pressure that the triple valves on every wagon are monitoring simultaneously. And the engineer is watching a set of gauges and making decisions that keep 15,000 tons of coal moving at a controlled speed down a grade that gravity is continuously trying to accelerate. The air brakes work. They work perfectly in their role. That role is just not the one most people assume it is. And the real story of how a heavy freight train descends a mountain is considerably more interesting than the simple answer suggests. If you enjoy the engineering that keeps these machines running, subscribe, because every week there is another layer of this to uncover.